All right, everyone. So here we have chapter 20, which will be on second law of thermodynamics, or different versions of the second law of thermodynamics. So previous chapter, like chapter 17, I think we introduced um, for a zeroth law of thermodynamics, and the previous chapter we learned about first law of thermodynamics, and here we're going to talk about the second law of thermodynamics and briefly mention the third law of thermodynamics at the very end. So, kind of like the units for this chapter, one of the ways we can describe or define the second law of thermodynamics. Now, one thing you will see is that the second law of thermodynamics can be described in at least like half a dozen different ways. So we're going to be able to describe that in terms of, let's say, the heat engines, in terms of the efficiency, in terms of the Carnot engine, in terms of entropy. So those are, number of ways we're going to see that we'll be able to describe the second law of thermodynamics. But the we're going to start with one of the definitions, and then we're going to be able to use that to describe heat engines. Then we'll talk about the processes that can be either reversible or irreversible, and we're going to talk about specifically a Carnot engine and also Otto engine, Otto cycle. We're going to talk about those two to describe, let's say, more theoretical, especially Carnot engine, right? The more theoretical, let's say, type of engine, and use that to sort of like, let's say, uh, talk about the maybe like, let's say, maximum theoretical efficiency or the engine can have, and then kind of compare that to real type of engines. Then we'll talk about refrigerators and air conditioners and heat pumps, which are kind of like, let's say, opposite of the heat engines. So we're going to talk about, the differences between, this type of devices, right? The refrigerator, air conditioner, heat pumps, and what is the main difference between those and, let's say, the heat engine. And obviously, there's a difference in a way that the energy is flowing. In heat engines is going to go from hot to cold, and we're going to extract some of that energy to do useful work. Where in the refrigerators, air conditioners, or heat pumps, then heat going to go from cold to hot, but we're going to have to, like, input some energy in order for that to happen. Then we'll talk about the entropy. So the entropy is another, state variable that we're going to introduce in this chapter. We're going to talk about how we can describe the second law using the entropy, and how the entropy then can be used to um, relate that to for example, the heat and temperature, and then, let's say, use it to describe sort of like, let's say, this concept of order disorder, because entropy is sort of like, let's say, as I said, right, a state variable. We can use that to relate that to, especially, let's say, for example, temperature, and it's one of those quantities that sometimes becomes, a little bit, statistical, probabilistic, and we're going to look at, in terms of something like that as well. So why, for example, the entropy of the system either always stays the same or increases. We're going to look at conditions for those, and we're going to talk about unavailability of energy, heat death, statistical interpretation, as I said, right, statistical interpretation of entropy, and the second law. Then thermodynamic temperature and third law of thermodynamics. So in a way, this last two parts over here, more of like a for your information. So we're not really going to be, diving too deeply into those concepts. The third law of thermodynamics, I'll just give the definition, just basically give you an example, but not necessarily, go to great, details into those things. All right, so let's then start with one of the ways we can describe the, let's say, second law of thermodynamics. Let's start with something like this. So let's say, remember the first law of thermodynamics. Okay, so it's an energy conservation. Okay, so energy conservation means that when changing thermal energy of the system, if there's a change in thermal energy, then you can say that that's related to changing thermal energy, right? It's pretty much directly proportional to change in temperature. Okay, and then what you have here is that change in internal energy also equals then Q heat added or removed minus the work done by the gas. So by, let me put it like that, by the gas. Because if you're doing the work done on the gas, then it becomes Q plus W. Okay, so this represents in terms of uh, change in thermal energy or the conservation of energy. Okay, that means energy is conserved. Okay, now one of the ways we have here is, so you can see that when you look at from one state to another, so here's our initial state. So can we see something like this in nature or not? Okay, so think like this. You have this cup on the table. That's the initial state. Then it goes down, hits the floor, and breaks into pieces. That's basically one process. Is the reverse of that possible or not? Can you sort of like, let's say, have the cup, which is initially in small pieces, then resembles itself, rises up, and becomes a cup again? All right. So according to basically, like, let's say, our calculation and theory and things like that, it's possible. You know, that means you can have something in reverse and energy still be conserved. But does it happen in real life? Okay. Can we observe it? Can, let's say, those pieces of cup spontaneously on their own go and become a full cup again? Okay. So that's something that we're going to be able to, talk about in this chapter. That means reversible versus irreversible processes, under which condition process can be reversible, under which conditions irreversible, and what are the differences between them. So those are basically something like that we can see. Okay. Now, about something like this, then, the second law of thermodynamics states, okay, in terms of which processes can occur and which is not. That means, for example, cup on a table goes down, hits the floor, breaks down into pieces. That's a process. Can that happen? Yes, it can happen. Can that happen spontaneously? Yes, that can happen, right? It can go down and hit the ground and break. Okay. But then the reverse, will that happen? Well, not so quite, right? So it will not happen in terms of just on its own going up and reassembling itself and becoming a cup again. So same thing in terms of, let's say, thermodynamic process, when changing thermal energy in terms of heat and work done. So here's, for example, one of the ways we can describe the second law. Heat can flow spontaneously from a hot object to a cold object. Okay, that's a process that we have seen happens. Okay, it will not flow spontaneously from a cold object to a hot object. That means this does not happen. Okay, and again, the word here is spontaneously, which means if you let the system, basically on its own, right, this will allow the system, the heat, right, go from hot to cold. Okay, on its own, nothing needs to be added, no work needs to be done. It will go from hot to cold, but not other way around. Okay, that's what you can see, right? Will not spontaneously go from a cold to hot object. In a way, one of the ways we can describe the second law is that it gives us direction, in which direction the heat is flowing. And it's a law. That means we can take that as given and assume that heat will go from hot to cold, but it will not go from cold to hot. Okay. So, and that's a very important implication, right? So that means whenever you are, you know, designing something like, let's say, heat engine or a refrigerator or something like that, then you have to take this into account. That means, some things, let's say you can do, some things you can't. And for example, you can't build a refrigerator and expect that, without doing anything else, right, it will just basically the energy will go from cold to hot. We're going to see that in order for that to happen, right, let's say for a refrigerator that, let's say takes heat from cold and moves it to hot, what we call reservoirs, right, we have to, do something extra. Okay. Where, for example, a heat engine can just sit there and have the energy go from hot to cold and then use that energy in the process to do some kind of useful work. All right. So let's then talk about those heat engines. Okay. So the heat engine is basically, the first sentence in that statement, which is that heat spontaneously will go from hot to cold. That means if you have two reservoirs, so let's say here's a hot reservoir. Hot reservoir means it has a temperature, let's say TH. And then you have a cold reservoir, something that has a lower temperature. So you might see me either writing TC, T cold, or TL, T low temperature. So both kind of like the same thing for me. Just in some examples I'm using TL, in some examples I'm using TC. So make sure that you guys are aware of that. That's the notation, just representing same thing, cold or low temperature reservoir. Okay. Now, one thing we have here is this. I have basically hot reservoir, cold reservoir, and if you put something between them, some kind of conducting material or something like that, then on its own, because TH is greater than TC, for example, right? Because it's, they're in contact, sort of like, let's say we can either do allow the heat transfer to go, as a conduction, convection, or radiation, like we learned in the previous chapter, right? There are three different ways we can, three different, let's say, transfer mechanisms. So let's say this is, conduction. That means there's some kind of, conducting material connecting them. Then, because the difference in temperature, heat will go from hot to cold. Okay, heat will go from hot to cold. Then what we do is we put an engine here. That means we put engine exactly between them. We put engine exactly between that, in that path, right, of the heat. So then what we can see here is this QH is the energy exiting, or, basically entering, my engine. That means exiting the hot reservoir, but, entering our engine. So then this QH, this amount of energy that comes into my engine, okay, then I can take that energy and use some of that energy inside my engine to do some kind of useful work. That means I can redirect some of that energy to do a useful work. Okay. But one thing we're going to see here is, which basically one of the versions of the second law of thermodynamics, is that if we take that energy, right, from hot to cold, that basically the energy that goes from hot to cold, we take some of that energy and we use that to do work. Some of that energy will always then be, let's say, it will go toward the cold reservoir, so like a waste energy. So some of that will be dumped out into the low temperature reservoir or cold reservoir. That means we have three quantities, okay, in terms of, let's say energy, right? So QH represents amount of energy basically entering the heat engine. QL or QC is, okay, so let's say QL or QC, kind of same thing. This will be the amount of energy exiting, basically dumped out of the heat engine that goes into the low reservoir. And then W then is the amount of work that we basically able to convert from QH into useful work. Okay, so that means some kind of useful, I don't know, that's energy that goes into some kind of useful work, maybe like a heat pump or something like that that can be used. Maybe like, let's say, I don't know, the wind turbines or something like that that we can use. So we'll see that in the next slide. I can't talk about that. So this is basically a basic picture of a heat engine. Okay, that means we use um, some kind of energy that's already going on its own, right? It's already moving from hot to cold. We don't have to do anything about this. We just put our engine exactly in the path of that heat flow. So then when heat enters the engine, then we can use that to get some useful work out of that. Okay, so we're going to talk about that, right? So we will discuss only engines that run in repeating cycle. The change in internal energy over a cycle is zero, okay, as the system returns to its initial state. And this should make sense, right? For example, if you have a PV diagram, if this is your initial state, so let's say here's your state 2, maybe state 3. Let's say it goes from here to there, from here to there, and then comes back. So that's kind of like what cycle looks like, right? So cycle means you come back to the same point. Well, same point has the same temperature. That means there was no change in temperature. Well, if there is no change in temperature, there is no change in internal energy because they're directly related to one another. That's why internal energy over a cycle is zero, because it returns to its initial state. Now, the high temperature reservoir transfers amount of energy QH, as we mentioned, right? And part of it is transformed or converted to the work. The rest, QL or QC, is exhausted or dumped into a lower temperature reservoir. Okay. So now what we do here is we take all those quantities to be positive. Okay, all those quantities to be positive. And what we have here is this. Let's look at this example of a steam engine. Okay, so here is my hot reservoir. That means what I have here is I have a boiler where I take a certain amount of water and I, basically have some kind of heat output, put it on a hot plate or something like that, right? So basically there's some kind of, way of evaporating some of that water into steam, basically boiling out. Um, so that means I have like TH. Remember, when you start boiling, right, that you can say that during that when it's boiling, this temperature pretty much constant because water and steam are in equilibrium. So then you have water and steam over here. Then the steam here will travel from here. So let's say here we have some kind of low temperature reservoir. So on its own, it will go from here to there. Okay. Then what we do, we put some kind of engine here. Okay, so it says, so basically we have an intake valve that open during expansion and exhaust valve closed during the expansion. That means what we have here is that as this steam travels and enters this basically our steam engine, it then will take some of that energy, right? So you can see, right? So the turbine, boiler, and condenser are not shown, but what you have here is as energy enters, pretty much in this region over here, right, in the steam engine, some of that energy is used to, you know, basically rotate the turbine inside. Okay, which then does some kind of the piston does some kind of useful work. Okay, rotate something or something like that. Okay, then some of the energy that exhaust valve, right, some of that energy then will dump the rest of them into this what we call low or cold reservoir. Okay, where we have actually condenser then takes the steam and condenses into water. Then we have a water pump that moves the water to the boiler and basically repeat the cycle. That means this is basically, you can see, right? It's a repeating cycle. So overall in the system, changing internal energy is, doesn't change, right? It's constant. And changing internal energy is basically zero, right? And what we do here is this energy that, will go from here to there, right? Here in the steam engine will be converted into some kind of useful work. Okay, so the turbine will be rotating and things like that. So that's kind of like the basis of that. All right, so the same way we can think of, like, let's say in terms of internal combustion engine. Okay, it's a type of heat engine as well. Okay, so let's see what we have here. All right, so here let's look at first, starting from on the left side. All right, so we have here is this. So first you can see, right, you have a gas air mixture from carburetor. So entering, so there's an intake valve and it's open. So we basically have the gasoline air mixture flows into the cylinder as the piston then starts moving down. Okay, because you have more matter coming in, right? So it basically pushes the piston down. Then what we have here is that you can see, right, there's two valves, intake valve and exhaust valve. So when the intake valve is open, exhaust is closed. That means the matter is entering, but nothing is exiting. As the matter enters, then those gases, right, they push down the cylinder. Okay, so now we have here is what we take, basically there's an intake portion, then we have a compression. Okay, so you can see, right, when the gases are pushing the piston down, so you have this connecting rod, and it's basically as it's going down, the piston is rotating this crankshaft. Okay, now what we have here is for the second one, when there's a compression, so you have a piston basically as it kind of like already goes all the way down, right? And let's say this crankshaft rotating as it going starts continue rotating clockwise, it then pushes the piston up. Okay, that means here we have piston basically starts moving upward and starts compressing the gas. Okay, so then because the both valves are closed, right, as it pushes the gases, right, upward, compresses them. Well, when you compress, what you do without, let's say you assume it's a closed system, and you have a compression, well, the gases are nowhere else to go. So you compressing them, which means the pressure increases. Well, as the pressure increases, temperature increases. Okay, and you can see, right? So when you really compress them, pressure increases to a really high, value, and then the temperature increases. That means it increases so much that then you can basically get some kind of ignition. Okay, that means the instant, right? Those, let's say the firing the spark plug, right, ignites the highly compressed gasoline because you're really compressing them. So then the temperature increases, and then you basically get a spark. Okay, so after that, gas is now at higher temperature. Okay, and what you have here is now you have a high temperature and pressure, and it's expand against the piston in this, power stroke. That means basically because of the spark, right? So you get the high pressure, high temperature, and then they continue, right? Then they're pushing it down. So then now you have, the rings, right? So basically that you get, again, instead of having the air coming in, the gases coming in, right? So you already have, because of the spark, even more increase the temperature. So then just basically temperature, pressure increases, and you have expansion. Okay. After that, we have exhaust valve opening. Okay. And as we open it, then the all those molecules, let's say mixture of gas air, mixture that we had now becomes basically too much burned gas. So what we have, when you open it, right, they're pushed out of that exhaust pipe. Okay. So when then they are pushed, right, then the piston basically pretty much, you can see, right, again, goes all the way up. So it pushes them, it reaches the top, then exhaust valve closes, then intake valve opens, and we basically go back to the same, cycle that repeats. That means we have intake of gas mixture from a carburetor, then we're compressing them, then basically, burning them, right? And then pretty much that's what, so it's an internal combustion, right? So then we then opening the exhaust valve and then basically sending them away pretty much to the some to some kind of way of like to some kind of exhaust valve. Okay, so during this process, then the engine partially converts the energy from combustion to work. All right, now one important thing about this for any heat engine is that it requires a temperature difference, right? So you can say, why does a heat engine need a temperature difference? Well, think about it, right? So if you don't have any, change in temperature, then heat will not go from, one reservoir to another. Okay. So, and otherwise the work done on the system in one part of the cycle would be equal to the work done by the other system, by the system on the other part, and the net work would be zero. Plus the heat flow always requires different temperature, right? So we know that from the zeroth law of thermodynamics that if you have two systems in contact and they have the same temperature, then there is no heat flow between them. One of the things we can do about heat engines is to calculate their efficiency. So efficiency of a heat flow, uh, basically efficiency of the heat engine in terms of that heat flow to the engine and then out of the engine is defined as the useful work that we can extract out of how much basically we get. QH represents amount of energy entering the steam engine. W represents amount of energy that was converted to a useful work. That means W over QH gives you the efficiency. So for example, let's say here's a simple heat engine. So this is basically TH, and let's say this is TC, some kind of hot cold reservoir. And let's say we put some kind of engine over here that takes some of the energy. So let's say we have QH is equals to 100 joules. And then out of that, we do useful work of, let's say, 40 joules. Well, that means then 60 joules goes into a cold reservoir. That means what we get here is we get 40 joules of useful amount of energy out of 100 joules that was available to us. And this is basically zero point 0.4. And usually what we do is we multiply this by 100% to get some kind of percentage. So in this case, uh, it will be, let's say, 40% efficiency. So 40% efficiency means that, this engine, right, can extract 40% of any type of energy that enters the engine, right, into a useful work. But 60% of it is pretty much exhausted. And you will see that roughly this 40% is maybe like the let's say even can be considered as efficient let's say engine. Generally the efficiency is very low for example cars and things like that. The typical car has an efficiency of maybe 20%, 25%, depending, let's say what car are you talking about. But generally, let's say 30-40%, we're going to see that can be considered as a relatively good, efficient engine. Okay, so other ways we can represent this equation is this. So W is the work done, which we can see, right? So out of 100 joules, 40 joules is the amount of converted, energy, and 60 joules is basically the amount of exhaust energy. And we can see that W is basically the difference between QH and QC, or QL, right? Q low. Again, remember, QC and QL are pretty much the same. That means there's a difference between that. So if I replace W with that difference, QH minus QL divided by QH, then I can take that, represent as just 1, then minus QL over QH. That means this is just another way of writing the efficiency. So 1 minus QL over QH. Okay, the ratio of QL over QH, 1 minus that gives you, again, you need to multiply that by 100% to get the percentage. But it just a couple of ways that you can represent that efficiency depending on what you have. Because if you're given the differences between the QH and QL, you can just use this equation and calculate the efficiency. All right, so now that we know a little bit about heat engines, we can then talk about this. And I'm sure some of you maybe maybe they were thinking, like, how come we can't get 100% efficiency? That means how come we cannot get 100 joules and convert it all to a useful work of 100 joules? Well, it's not possible. And that's basically another way we can write the second law of thermodynamics. Okay, that means in terms of efficiency of the heat engine. So no heat engine can have efficiency of 100%. This is another way of we can write it. So, and this basically statement says that no device is possible whose sole effect is to transform a given amount of heat completely into work. That means you have a hot reservoir at the temperature of TH, and then you get heat, which is QH, and then we cannot take that QH and convert it into useful work, which will you can see, right? If you have E is equals to W over QH, if all the work is converted, so you have then QH over QH, you get 100%. Basically, you get 1 and then multiplied by 100%, you get 100%. That's 100% efficiency. Means that QH is equals to your W. But according to second law of thermodynamics, no such engine exists. Okay, so we'll talk about, let's say, why that's the case, and we're going to talk about, let's say, some of the theoretical maximum possible efficiency that engines can have, because there are technically some engines that theoretically possible but practically not. So but they're still useful, let's say, in a sense that we can use them to do some calculations, even though we can't really build those type of engines. Okay. So let's look at a few examples here. There's a efficiency of an engine. Let's take an engine that transfers 2 times 10 to the 3 joules of energy, so basically 2000 joules of energy, from a hot reservoir during a cycle, and transfers 1.5 times 10 to the 3 joules as exhaust to a cold reservoir. Okay, so that means we have some kind of heat engine that we know amount of energy that goes into that, like this is QH, and then it transfers um, some of the energy into work, and then 1.5 times 10 to the 3 joules goes into exhaust to a cold reservoir. Okay, that means we're given pretty much our QH and our QC. Okay, so then find the efficiency of the engine. Okay, so you can see, right? So like here's the image of that engine. So you have hot reservoir, and then we put some kind of heat engine over here. Remember, so even if that heat engine was not there, right? So the energy would go from hot to cold spontaneously, but it will take all the 2,000 joules of energy from hot to cold. It just when you put the engine, it can take some of that energy and convert to work. Okay, and this engine has efficiency of 1 minus Q, let's say QC over QH, which becomes 1 minus so 1.5 times 10 to the 3. So I can just write 1500 joules over 2000 joules. So units cancel out. And what I end up here is um, 0.250, which and then I multiply by 100% to get 25%. So 25% is then the efficiency of this engine. Okay, so that's for part A. Part B is then it's asking, all right, so how much work does this engine do in one cycle? I mean, obviously, it's a simple, calculation, because we know then the work done is just a difference between, QC and QH, right? So QH minus QC will be equals to, remember what we do is we always assume that those values are constant. So make sure that, to make sure that they're using always positive values, we can put absolute value. So you can say that 2000 joules minus 1500 joules uh, to get basically 500 joules as a difference between those two reservoirs. That means work done is 500 joules. Okay, as you can see, right? Um, this engine is about 25% efficiency. That means for every 100 joules, 75 joules, let's say, will go into waste, and only 25 joules of energy will go into doing some kind of useful work. All right, here's one more example. Suppose you were asked for the power output of this engine. I just continuing the same example, sorry. Do you have a sufficient information to answer this question? That means, what is the power output of this engine? Okay. Well, let's see what we have. In terms of equation for power, if you remember, power is equals to change in energy over time, or amount of work done over time. Okay. So we just calculated that information for the work. It was 500 joules, but we don't have anything about time, because we were not told anything about how long did it take for the engine to extract that 500 joules of energy. That means for this example, right, for this particular part, we can't. So we need to know, remember, this is still a sort of like a repeating cycle. We are, looking at the processes that basically repeat itself, but still, I don't know how long did it take for that, let's say, uh, cycle, right? How long did it take for that cycle to happen? The process requires, the calculation of the power, right? This one requires, to know the time. For example, let's say if you were given the time for a cycle, let's say 30 milliseconds, then we could calculate the power here. So 500 joules divided by, let's say, 30 milliseconds. Then we could calculate, for example, 17 kilowatts. Okay. And this would have been in terms of the power output, right? So how many joules each second and things like that. So, in terms of here, for the calculation of power, you need, and the work done and the time for the cycle. All right. Okay. Here's one more example here. A cycle consists of three processes. So we're going to make a table with rows labeled A, C, A to C, and basically you have a process that goes from A to B, B to C, uh, and then back from C to A. So we're going to make a table which you can see right now, and columns labeled changing thermal energy, work done, and amount of heat energy that was transferred in or out. So fill each box in the table with plus, minus, or zero to indicate whether the quantity increases, decreases, or stays the same during the process. All right, so let's see. Well, I already have the table pre-built, so we can see, let's say, what's going on here in terms of thermal energy, work done, and Q for, let's say, each three parts of the process, the system. That means this is, again, it's a repeating cycle, right? We're coming back to point A, but let's look at it in terms of going from A to B. Okay, going from A to B, we're told that it's adiabatic. Okay, well, remember, adiabatic means that um, no heat transferred. So there is a reason that uh, for A, that means the path A, which is going from A to B, the Q equals zero. Okay. Now we're pretty much looking at this, right? So we have a change in internal energy is equals to Q minus W, which is the work done by the gas. So for the A, Q equals zero. That means change in internal energy is equals to negative of the work done by the gas. Okay. Now, um, what we have here is this positive or negative? So because if you look at this equation, it seems like this guy here is positive, this is negative, but that's not the case, right? So what we have here is, the work done by the gas is positive because you have an expansion, right? So you have a volume one here and volume two here, and volume increases. Volume increases means work done by the gas here is positive. But when the volume increases, internal energy will then decrease, right? Because every time you have a adiabatic expansion, you are decreasing temperature. You're decreasing temperature, then internal energy increases. So that's why work done, you know, uh, this is S stands for work done by the system or by the gas, right? And it's positive, and change in internal energy is negative because we go from higher temperature to lower temperature, right? So we decrease the temperature. We can, which you can also see that from the equation over here. All right, so that's for A. For the B, then we go from basically, this I guess, I would say, if this is A, this is B, this is C in terms of points. Maybe we can just change it a little bit, right? So let's say this is for path B, but let's say I put like points 1, 2, and 3, like that. So imagine we're going 2 to 3, taking the path B. Okay, so well, it's a path that doesn't change any volume. Remember, so there are two ways we can represent that. It's either isochoric or isovolumetric. Just representing two things, just two different ways of writing the same type of process. Well, during this process, your volume doesn't change, right? I mean, volume 2 and volume 3 are exactly the same. So if delta V is 0, that means work done is 0. Remember, right? That means, we have no work done. That's why for path B, there is no work done. Then change in internal energy is equal to then Q minus work done by the gas. And this is just 0. So Q is equal to the, change in, Q is the amount of energy transferred, into the system. And change in internal energy is positive. And this just obvious, it should be obvious from the points 2 and 3, is that point 3 has a higher temperature, right? It's at the higher isotherm, and that means this energy here is positive because it enters the system. That's why energy, entering system increases temperature. But then since temperature increases, change in internal energy will also increase because they're directly proportional. So Q is positive, change in internal energy is also positive, and W is negative. W is 0 for path B. All right, so finally we have path C, which is isothermal. Well, isothermal means temperature is the same. That means this means that T2 is same as T1, right? Because we go back to point one, state one, and temperature is exactly the same because it's along the same isotherm. Now, delta T means 0, which means then change in internal energy, remember, which is equals to 3 halves NR delta T, then it's also equals to 0. Okay, so that's what you can see, right? Change in internal energy is 0. Well, if change in internal energy is 0, then this is equals to Q minus W by the gas. That means Q and W are exactly the same. Okay. Now, in terms of what we have here is, are they positive or are they negative? Well, let's see what we have. We go from B to, let's say we go from state 3 to state 1, and we technically have a compression. Compression means that work done by the gas is negative for compression. Well, if the work done is negative, then Q automatically is negative. That's why it's negative, negative for each one of them. Okay. All right. So hopefully you guys were able to see that this is basically a repeating, a cycle like that. Here's one more example. So we are looking at some kind of process where we have a PV diagram. So we're given everything in terms of PV diagram. So we have, let's say we can say that we have W out. And so for example, for this particular, let's say processes, right, that we have, what are W out and QC, and also then the thermal efficiency for this heat engine. So this is some kind of heat engine where we are given basically 30 joules entering during one process, then 84 joule entering during another process, and then we're given the pressure. Let's use this. Let's say 1, 2, and 3. So you go from 1 to 2, 2 to 3, then 3 to 1. So we, in a way, we go given pretty much most of the state variables, right? So we're given, let's say, P1, that's 200 kilopascal. P2 is 400 kilopascal. And that's basically same as technically P3, because going from 2 to 3 is isobaric. Then we have a volume. So volume 1 is given 100 cubic centimeters. Volume 2 is the same as volume 1. And then volume 3 is given as 200 cubic centimeters. So we're given those values. Okay. Now, in terms of then what we have is we can look at, let's say, the work done, right, by the heat engine per cycle. And for the heat engines, that's basically the area under the graph. So pretty much this area under the graph. Those we can say the work, this W out, right, is equals to area under the graph, which we can do, let's say, 1/2 times pressure, which is, change in pressure is 200 kilopascal. And then change in volume is then 100 cubic centimeters, which we convert into 100 times 10 to the negative 6 cubic meters. Okay, so technically, remember, right, so here kilo must be in terms of times 10 to the 3 Pascal. Okay, so we can calculate this to be then 10 joules. Okay, that means for part A, which is this, that means work done is always, because it's a repeating cycle, right? That means, you start from 1, go back to 1. The area of your basically enclosed by the by your processes is the amount of work done. Okay, so which is in this case, 100 joules. Now let's see then what we have. That's part A, which is amount of work done. And then, sorry, part A is also asking for QC, which is, how much of that energy will be then dumped out. Well, let's see. I have the work done, 10 joules. Then in order for me to find QC, remember QC is equals to then QH minus amount of work done, right? So I have work done. I don't directly have QH given in the problem, but it's given in the diagram. That means we have 30 joules at one point, 84 joules at another point. That means overall we have 114 joules entering a system. Okay, that means 114 joules is my QH, then minus 10 joules is my work done. So then what we get here is 104 joules. Okay, so 104 joules is then my, QC. 10 joules is my then work done. All right, so part B says then, what is the thermal efficiency for this heat engine? Well, we can see that probably right away that it's not very, efficient, because out of 114, only 10 joules was converted into useful work. But let's calculate this. So efficiency is equals to, we can use this one, right? Work over, QH. So then 10 joules over 114 joules times 100%. We can calculate this to be 8.8%. So it's, relatively inefficient, engine. So it's only 8.8% of the energy can be converted into useful work. All right, so next we're going to look at reversible versus irreversible processes. So generally we can think of it like this. Reversible process is when the system undergoing process that can be returned to its initial conditions along the same path of a PV diagram. That means if you have something like this is state one, this is state two, whatever that path it is, right? So let's say something like that. So you go from one to two, and then you come back from two to one. That means the same path on a PV diagram. So that's a reversible, reversible process. Now, we assume that also that every point along the path is then equilibrium state. Okay. So generally, this type of processes that are defined to be reversible require very long time. That means basically, if you think of it as, it's happening very slowly, then you can break it down and think of it like let's say at any time your system is basically along that path is in equilibrium state. Okay. Now, anything that does not satisfy this is pretty much can be considered as irreversible. And reversible processes are actually very just purely theoretical. All the natural processes are irreversible. So, question is that why do we then care about reversible processes that if we cannot make it, as a sort of like some kind of engine or something like that? Uh, that's a good question. But the idea here is even if we cannot have a process or a system that is, a pure 100% reversible, we can still use the concept, the theory, the equations for the reversible processes to calculate something about the state. Because whatever I calculate about state two using reversible processes, the equations and the concept, same thing will be then applied to the irreversible process. Okay. One good example of a reversible process here is adiabatic free expansion of gas. Okay. So irreversible process, sorry. So cannot be reversible. So let's see what we have over here. So we have a gas that is thermally insulated in the container. So basically right here we have a container. We have some gas at initial temperature. And we can assume that, again, it's thermally insulated. So with an insulating wall, and there's a membrane here that separates gas from vacuum. That means in this region we have vacuum, here we have gas, and there is this membrane over here that kind of separates them. Okay. Now, one thing we're going to do here is, let's say, find a way to get rid of that membrane, puncture the membrane. And if we do, when it's punctured, then gas will expand freely into the vacuum. That means the system will change. It's going to occupy greater volume after expansion. Now, gas does not exert force through this displacement. It does not work because, it doesn't push any piston or anything like that. So it does not work on the surroundings as it expands. So at all times, we can think of, like, let's say that W equals 0. There is no work done. Also, because of it's insulated from its environment, then Q is equals to 0. No heat added or removed. So its container is completely insulated from the surroundings. It's an isolated system. Well, if we then talk about then changing internal energy, which is Q minus W, work done by the gas, if both of them are 0, then changing internal energy will be 0. That means internal energy of the system does not change, which means that the temperature is the same. That means Ti is equals to Tf. Temperature is same before and after. That means after the expansion, you get still the same temperature because no work done, no heat added or removed. So the system has changed. We have a greater volume. Greater volume, system has changed, but surroundings have not. Okay. Now, so this is an example of basically irreversible process. For the process to be reversible, we must return gas to original volume and temperature without changing surroundings. Okay. Now, imagine if we try to do that, what we'll have here is we need to compress, right? Remember, so once we puncture the membrane, so you have gas pretty much in all of this region, right? So basically where we used to have vacuum, now there's a gas. In order for us to move the gas to its original volume, well, we have to push down the piston. Okay, so we have to force the piston inward. That means surroundings change because work is being done by the outside agent or system. It's not going to go down on its own, right? So you have to just take it and push it down, push it inward. So the system changes because compression increases temperature of gas, because as you're compressing, the pressure changes because the volume changes, and then the temperature changes, right? That means what you have here is just doing that work by pushing the piston inward, we are increasing the temperature, which should make sense, right? Whenever you have a compression, the temperature increases. Now, one thing we can do here is we can lower the temperature by allowing gas to come into contact with some external, energy reservoir. That means, for example, if we put this on some kind of cold bath and allow the energy to move from our system to surroundings, right? So we can technically lower the temperature. Now, this step will return the gas to its original condition. That means if we do work and move the piston all the way here, which then we get sort of like, let's say, our original volume, right? We get our original volume from the, volume that we, let me put like V prime, right? The volume that we get after we puncture the membrane. But in order for it to do that, we have to do work. Then we have to remove the heat. But basically what we have here is to get this, right? To return the gas to its original conditions, surroundings again, affected because energy being added to surrounding from gas. That means what I have is that I have to remove energy from this, right? So this, I can get rid of this for now. So the energy is removed from the gas, but then where does the energy go? Well, it goes to the surroundings. Okay, that means the surroundings are affected by the removal of the gas of the heat from the gas. Okay. Now, if energy could be used to drive engines that compresses the gas, then net energy transfer to surroundings would be 0. And the system and its surroundings could be returned to its initial conditions. And that's, if we can achieve all that, then this will be a reversible process. Okay. Now you can see, for now, what we have here is one statement about the Kelvin Planck statement of second law, a different version of the second law that specifies that energy removed from gas to return temperature to original value cannot be completely converted to mechanical energy by process of work done by engine in compressing gas. Directly related to this, example that I just we were, talking about. That means when you remove the gas, right? When you remove the gas to return the temperature to original volume, because when we push the piston inward, temperature increases. In order for us to return the temperature to original volume, we have to remove gas. Okay, but once you remove, right, the value, you cannot completely convert the mechanical energy, cannot be completely converted to mechanical energy by a process of work done by engine in compressing gas. Okay, that means how much work you do, how much heat is added, they're not the same. Okay, because once the energy technically goes to heat, some of the energy cannot be converted back. So the conclusion here, the process is irreversible. All right. So this is again this Kelvin Planck statement of second law. Now, some processes, some real processes, almost reversible. So as I mentioned, right. So when you talk about reversible processes, this is highly theoretical, and we have to talk about, like, let's say in terms of them not being real, right? So you cannot, you know, generate, or you cannot make an engine that can be irreversible. But some of them can be close to being reversible, and as I mentioned, it requires the time for the process to take a very to be very large, very long time. So it occur if it happens very slowly, that means you're doing very slowly and take your time. Then you can think of like you're very nearly in equilibrium state. Okay, and then it can be approximated as being reversible. Okay. Now, the general characteristics of a reversible process, again, the idea is that no non-conservative effects. Again, why is the work done, for example, is not the same as the amount of heat removed? Because of the some kind of friction. That means when you do work, some of that work goes into heating up the surface of the container and things like that, those walls of the container. So there are always a non-conservative effects, turbulence, friction, that will transform mechanical energy to internal energy. Uh, and what we have is that that's most of the time impossible to eliminate completely. So that's why real processes in nature are irreversible. There is no such thing as frictionless surface, right? There's no such thing as frictionless walls and things like that. So that means your system will always include some kind of non-conservative effect, as small as it is, that will make your uh, process as irreversible. So that means at this point, hopefully, it's clear in terms of reversible or irreversible. So one more example, you can think of like this, right? If you put a drop of food coloring into a glass of water, okay, you can observe that food color diffuse slowly out into the liquid. Okay. The irreversible process going on is diffusion. We talked about diffusion. So the food coloring, right, going to spread out, diffuse, and what you have here is that this process is irreversible because you can never see the full coloring spontaneously diffuse back into a single droplet, right? So that's basically an example of irreversible process. You can see diffuse, basically irreversible process, using the diffusion, but you can never see it go other way around. All right, so that's kind of like what we have. And the key word here is basically spontaneous, right? It's important to understand that we're talking about in terms of, so the spontaneous, because we talk about, like, let's say this equilibrium states of a system. In order to find those places of equilibrium, we need to be able to predict which processes are spontaneous and which ones are not. And second law of thermodynamics basically provides us with that. So some kind of theoretical criterion to let us determine which direction processes will occur. Okay. So here's one other process that we can look at that is, again, is theoretical, and we're going to talk about it was proposed by Sadi Carnot. So this is known as a Carnot engine. Okay. So this one was created to examine the efficiency of heat engines. Again, this is ideal sort of like scenario, right? So this idealized engine, assuming no friction. That's why it's idealized, right? There's no such thing technically as uh, no friction. But the idea for this particular Carnot engine is we can have, again, called a Carnot cycle. Oops. It's a Carnot cycle. So we start from A, system being at state A, with temperature TH. And then this particular engine, the Carnot engine, has four steps. So it's, this cycle consists of isothermal expansion from A to B. You can say it's isothermal extension because temperature of A and temperature of B are exactly the same. So it's isothermal. But what you have here is, because it's a expansion, your volume A is less than volume B. So what we have here, we have an isothermal expansion. Then step 2 would be adiabatic expansion, going from B to C. Remember, for adiabatic expansion, adiabatic means that no heat added or removed. But for the stage 1, where we have isothermal expansion, is there is a increase in volume. Now, why do we have heat added? Well, remember, if you are expanding your system, if the increasing the volume, well, we're decreasing the pressure. We can see, right, pressure is less for B at state B than compared to state A. So there's a less pressure. Well, less pressure means decrease in temperature. Well, we don't want the decrease in temperature, so we add heat to compensate for that. That means we want to make sure that temperature remains constant, even if the pressure decreases. The only way we can do that if we add heat into the system. And that's what happens. That means for the isothermal expansion, heat is added into the system. For step 2, right, for this adiabatic expansion, you can see, right, this is basically Q2. You can say that for step 2 is 0 because there is no heat added or removed. Okay, but obviously, you can see that volume changes. So system does work, right? Gases do work because there's a increase in volume. So gases do work, pressure decreases, but heat is not added. But obviously, if the system does work, system does positive work because it's a expansion, thermal energy, internal energy of the system will always decrease because whenever the system does work, it does work by removing energy out of the system, right? It uses some of the system of energy to do work. So internal energy of the system decreases and we have a lower temperature at point C. Then we have an isothermal compression going from C to D. Isothermal compression means that we are decreasing the volume, right? So our volume is decreased. So delta V is negative. And our pressure increases, right? So PC, PD, right? The pressure at point D is higher. But what we have here is it's an isothermal process, means the temperature doesn't change. We don't want the temperature to change. But volume is decreases, it's compressing. As the volume is decreases, pressure will increase, will then result in temperature increase. Well, we can compensate by removing energy out of the system. So then this QL represent, removing the energy out of the system, right? QL, Q at the lower, let's say reservoir. So then QL removes energy, keeping the temperature constant all the way to D. So then from D to A, then we have adiabatic compression. Adiabatic compression decreases the volume because, as the name suggests, compression. But remember again, so Q is 0 because it's adiabatic process. So if Q is 0, that means any change in volume directly goes to change the pressure. And what we have here is the pressure increases because the volume decreases. So you have adiabatic compression. So then the system there is a work done on the system, right? The work done whenever we have a compression is the work done on the system because some external agent pushes the piston inward. And what you have here, you have a higher temperature. As you compress, pressure increases, temperature increases, so you have a higher temperature at point A. And then the cycle repeats. All right. So then what we have here is this. Again, so there's another way we can look at this, a Carnot cycle. So the Carnot cycle for engine operating between temperature Tc and Th. We can see, right, that what we have two temperatures, two different temperatures. The Carnot cycle basically operates between those two temperatures. Okay. So assuming that we're working with a substance that is ideal gas and it's contained in a cylinder fitted with movable piston at one end. That means, so let's say we have a piston that is free to move up and down. Okay. So cylinder walls and piston thermally non-conducting. Okay. And what we want is the bottom, right, to be non-conducting. So the bottom to be conducting. So the cylinder walls and the piston are thermally non-conducting. That means they're good insulators, but the bottom not, because we won't be able to make contact uh, with some kind of energy reservoir that adds energy to the system or removes energy to the system. So as you said, right? So here we have TH. That means we're gonna basically start with some kind of heat added, right? So things like this. So this is sort of like, let's say, our A. So kind of looking at this PV diagram. So here's your one isotherm and here's your another isotherm. Okay. So let's say this was A. So we go from A to B. Remember, so we go A to B, and that's an isothermal process. That means isothermal process means that moving the piston upward, which means that volume increases because it's an isothermal expansion. But as we said, right, if you do that, the pressure will decrease. And the pressure decreases, the temperature decreases. So energy, basically heat added to the system. QH enters the system, so we add heat. Okay. Then what we have here is um, once you go to point B, from point B to C, then what you have here is you have adiabatic expansion. Adiabatic expansion means that, again, you're expanding your system, you're increasing the volume without adding heat. Without adding heat. And well, in this case, the temperature would decrease because, pressure decreases. And if the, pressure decreases, then temperature decreases. That means we get to this, uh, let's say this C, right, point C, where after that, what we do here is we lower the piston, move it, push it inward. And obviously, when we do that, it has a isothermal compression by removing the Q, because as you push it down, it compresses, pressure increases, temperature increases. But by removing heat, we keep temperature constant. Okay. Then finally, what we do here is we go from, let's say this was in terms of going from B to, I guess, B to C, then from C to D. Okay, then finally go to A, and that's a adiabatic compression. Okay, so this was adiabatic expansion. Now we have adiabatic compression, which means, undergoes an adiabatic compression. So we compressing without removing heat, allowing the temperature to increase to the original value. Okay, that means what we're doing here, we are repeating a cycle such that, our system comes back to the original state. That means this Carnot engine is basically a reversible process. And here's Sadi Carnot. He was a brilliant engineer. Unfortunately, he died very young, but he had major contribution to the this thermodynamics branch of physics. So here's what we have about Carnot engine. No real heat engine operating between two energy reservoirs, TH and TC, can be more efficient than a Carnot engine operating between the same two reservoirs. Now, the Carnot engine is a reversible engine, and it's a theoretical engine. That means it's, remember, so all the reversible are not real, right? So it's a, purely theoretical engine. And this statement says that no real engine can ever reach the same basically efficiency pretty much as the Carnot engine. right? They can never be more efficient than the Carnot engine operating between two same reservoirs. That means whenever you calculate the efficiency of a Carnot engine, then you can think of, like, let's say that could be pretty much considered as the maximum efficiency for that particular engine, because no real engine that you can create for the same, two temperature reservoirs between, operating between two temperature reservoirs will ever have the same efficiency. Here's a sample of some of his writings, and you can see, right, you know uh, the writing basically at the time was a little bit different compared to what you will see in the textbooks today. All right, so everyone knows that heat can produce motion, that is, possesses vast motive power, no one can doubt, in these days when the steam engine is everywhere so well known. Notwithstanding the satisfactory condition to which they have been brought today, their theory is very little understood. The question has often been raised whether the motive power of heat is abounded, or whether the possible improvements in steam engine can have an assignable limit. And that's kind of what we have, right? So he realized that there could be a limit to the efficiency of this type of engines. And this limit can be calculated using equations that more or less we already have seen. So for ideal reversible engine, the efficiency can be written as, so we have this equation right here, 1 minus QL over QH. So that's the efficiency of heat engine that we already seen. Now, one of the things we're going to see here is that QL over QH is equals to TL over TH. That means these ratios are equal to one another, which I will demonstrate you in an example. So this ratio of QL over QH, which is Q at the lower temperature reservoir over the Q at the higher temperature reservoir, is equal to the ratio of TL over TH. That means when you're talking about then replacing this with this ratio of the temperatures, then this becomes the ideal, efficiency of an ideal engine, like a Carnot engine. So 1 minus temperature at lower reservoir divided by temperature at the higher reservoir. So sometimes, as I said, right, it can be written as 1 minus TC over TA, different notation. So from this, we can see that in order for this engine, right, in order for this engine to have 100% efficiency, this term has to be zero. When is this term zero? Well, this is zero when TC equals zero. That means TC over TH equals zero only when the TC equals zero. Remember, this is the temperature given in Kelvin. TC equals zero means that we're talking about not 0 degrees Celsius, but 0 Kelvin, absolute zero. Okay. And we talked about that already. Technically, it's impossible. It is impossible for us to reach 0 Kelvin. Okay. Basically, reach absolute zero. That means it's impossible to have a 100% engine. That means whenever we have let's say, some kind of ideal engine that you can calculate efficiency, you can always assume that real engines will have even less efficiency, and none of them can ever have 100% efficiency. Generally, what we have is this. The real engines always going to have some kind of frictional losses, and their values, the efficiency, right, of real engines can never be greater than, let's say, 80% of the Carnot value efficiency. That means when I use this equation and calculate efficiency of some engine, theoretical engine, then the real engine that I used, they are, let's say, built based on this different, the same, let's say, temperature reservoir uh, that I used in the calculation, efficiency will be no more than, let's say, 80% of my calculated value. All right, so and that's kind of what we have, right? That means efficiency, real engines have always less efficiency than theoretical engines. But again, this type of calculations are very useful because most of the time, this type of calculations will help me get the value for the, let's say, value for state 2, and regardless, let's say, the path was taken. What I mean here is that So like the power of using this concept for the reversible processes is that the variables, right, that we use to analyze thermodynamic systems are always going to be state variables. Okay, so right. So for here, TLTH that I'm using to calculate is a state variable. Okay. Which means that if the final and initial states of a system are given, we know the values of those, then the calculation on those systems can be done with an arbitrary path. That means doesn't matter what is the path between that state one and state two. Okay, I can do the calculations, find the information about, let's say, what final state, and that will be independent of the way the system came to that state. Right. So that's the key. That means these calculations, even though purely theoretical, can be very useful. So let's look at then in terms of an example where we can see that the ratio of energy transfers by heat in a Carnot engine is equal to the ratio of reservoir temperature as given by QC over QH equals TC over TH. Again, QC is the cold reservoir heat, TC is a cold reservoir temperature, QH and TH represent hot reservoir. Okay, that means what we want to see here is prove that these ratios are equivalent. That's why if I'm then writing E is equals to 1 minus QC over QH, I can write this as same way as 1 minus TC over TH. That means, I can write both of those equations because the ratios of QC over QH will be equal to. All right. So let's see what we have. Let's imagine like we have some kind of isothermal expansion. Okay. So we have some kind of isothermal expansion, and we're going to find the energy transfer by heat from hot reservoir and, using the first law of thermodynamics. Remember that change in internal energy is equals to then Q right here. So it's Q minus work done by the gas. So I'm going to just let me do like a WS, which is work done by the system. Okay. If the work done is on the system, I can write as a WEXT, which is external work, or ON, which is on the system. Okay. So let's say we have this. Now, what I can do here is I can write this in terms of then, let's say if this is for the isothermal process. Remember, this is in terms of Carnot engine, right? So I have, let me kind of write it over here. So remember, so these are my isotherms. Here's one, and here's the other one. So what we did, we started from point A, and then we went to B. Okay, using isothermal expansion, right? So let me kind of do it like that. All right, so right there. So this is my, let's say, step one. And what I had here is, remember, that was QH, right? That was added into the system. So then what I can use here is I can calculate that QH using this equation, where QH is then equals to change in internal energy minus the work done going from A to B. Remember, this is the work done by the system, right? Because it's a isothermal expansion. All right. So now what I have here is there is no change in internal energy between A and B because same temperature. So this is zero. That means this is basically zero minus, I'm going to start putting absolute values. Remember, because QH and QC are always positive. So then zero. Okay. So 0 minus work done going from A to B, which is just going to be work done for A to B. Now, this QH, again, can be written as the work done for the isothermal process, which is going to be N times R times T temperature, which is temperature H, right? Because remember, so this is temperature H, this is temperature C. So the temperature is then times Ln of VB over VA. Okay. That means that's a heat added during that process. All right. So then same way, then I can, so when you have, remember, so there is no heat during this two processes, right? The adiabatic expansion and compression, but there's heat added during the third step, sorry, heat removed, right, during this third step. So this QC, okay. Then to calculate that, right, so this is QH. So QC then will be this. Similar way, QC is equals to, let me do it like this, change in internal energy minus work done. But this time, so let's say minus work done going from C to D. Again, no change in internal energy, so it's 0 minus work done C to B equals work done C to B. Okay, and this is basically, again, isothermal process, so NRTC ln of VC over VD. Okay, because this time it's a isothermal compression. Okay, and the work done is work is done on the system rather than by the system. Okay, so it's VC over VD. All right, so then what we do here, we say then, okay, so QC over QH as a ratio is equals to NRTC VC over VD, sorry, ln of VC over VD. Finally. Then this is divided by NRTH ln VB over VA. Okay. So you can see, right, NR and R are going to cancel out. And what we end up with is TC ln VC over VD divided by TH ln VB over VA. Okay. Now, from here, what we can do is go and use those B2C and D2A processes. That means this, second step and third step, fourth step in our Carnot cycle. Remember, those were adiabatic expansion and compression. That means what we have here is we're going to use them to find out what those ratios basically represent, how they're related to one another. So what we do here is this. So if I use that, again, adiabatic expansion and compression equations, then what I have here is this. Okay. TH times VB gamma minus 1. That's for the one of the processes. And this is equals to then TC, then VC gamma minus 1. That's basically for step 2. And then we have TH. Let me write right over here. So TH VA gamma minus 1 equals then TC VD gamma minus 1. Okay. Now, from here, then, we can do some algebra here. Okay. So we can kind of get rid of the temperatures, TH. If I divide those two together, I can get rid of the THTC. So we have then VB gamma minus 1 over VA gamma minus 1. So then VC gamma minus 1 over VD gamma minus 1. So then that ratio ends up being, since they all have exactly same exponent as well, they all end up being basically VB over VA equals VC over VD. That means those ratios are the same. That means, basically those exponents also cancel out and THs cancel out. That means the ratio of VB over VA is equals to ratio of VC over VD. And remember, what I have over here, I have then QC over QH is equals to TC ln VC over VD over TH ln VB over VA. But here then I'm saying those ratios are exactly the same. That means ratio at the top, VC over VD is same as VB over VA. So they also cancel. And you can see then this ratio of the Q is equal to then the ratio of the temperatures. Okay, so that's basically the proof that we can assume that the ratio of the heat added, heat removed versus heat added is equal to the TC over TH. All right, so here's one more example. So let's look at the steam engine. So you have a steam engine that has a boiler that operates at 500 Kelvin. The energy from the burning fuel changes water to steam, as we looked at earlier, and the steam then drives a piston. Okay. The cold reservoir temperature is that of the outside air, approximately 300 Kelvin. What is the maximum thermal efficiency of this steam engine? Okay. Now, what we're given here is we're given temperature of the hot reservoir, we're given temperature of the cold reservoir, and we want to find the maximum efficiency. That means we can use, this is sort of like, you can think like this is the maximum efficiency, right? Or ideal efficiency. So it's 1 minus TC over TH. So 1 minus, remember, if the temperature is not given in Kelvin, you need to convert them in Kelvin. So this is 300 Kelvin over 500 Kelvin. Using that, we get 0.4. Multiply this by 100%, so we get 40% efficiency. It means this, the steam engine has a 40% efficiency. Now, suppose we wish to increase the theoretical efficiency of this engine. This increase can be achieved by raising TH by some delta T or by decreasing TC by some delta T. That means the idea here is the efficiency will increase if the TC and TH difference is high. That means the temperature between those increases. Okay, that means you make your TH higher and TC even lower, and you have much bigger difference between those two temperatures of your reservoir, efficiency increases. Now the question is that which one will be more efficient? Okay, so let's see what we have. In terms of the value that we have, which is 40% efficiency with our original values, let's first do TH increasing by some delta T. So let's say efficiency is equals to 1 minus, keep this at 300, but increase this one by, let's say, 50 Kelvin. So it becomes 550 Kelvin. If we calculate this, we're going to get 0.455 0.455. Multiply this by 100%, we get 45.5% efficiency. That means we get 5.5% efficiency using 50 Kelvin higher temperature. Then, so this is basically TH plus delta T. Then let's do TC plus delta T. So 1 minus, now this is basically, sorry, TC minus delta T. So we remove, we decrease it a little bit. So 250 Kelvin over 500 Kelvin. So if we do that, then we're going to get 0.5 or 100% will give us 50%, 100% will give us 50% efficiency. Okay. Now, in terms of what we have here is we get higher efficiency when you decrease the temperature, lower, or your low reservoir by 50 Kelvin, then increasing your high reservoir by 50 Kelvin. So generally, as you can see, we get more efficiency by decreasing the lower temperature, but it is much, sort of like, let's say, more effective, right? So it's more feasible for us, for engineers, right, to make efficiency better by increasing the hotter temperature. Okay, it's always it's actually more feasible to do that than actually to lower the a cooler temperature. Another thing we have here is known as the Otto cycle. Is it's work with the automobiles. You can read automobiles run on the Otto cycle. They have two adiabatic paths alternating with two constant volume paths. So the gas enters the engine at point A and is ignited at point B. And curve CD is then the power stroke and DA is the exhaust. So, and efficiency of the Otto cycle is 1 minus the ratio of VA over VB times 1 minus gamma. Okay, so again, kind of similar to the Carnot engine in such a way that it's a cyclic, right? So you start with A, so you have then, you can say, right? So you have from A to B, then in this case, right? So you have, adiabatic. So there are no isothermal compression or expansion here. This is you basically have adiabatic, isochoric or isovolumetric, uh, where the heat is added or removed, because you need those, right? So you need one process where the heat enters, another one heat is dumped. But here is the difference is that let's call this path 1, it's a adiabatic, which means that there is no heat added or removed for this path. And path 3 is also adiabatic, which again, no heat exchange occurs. That means what we have here is this is a cycle that ends up having a ratio, the efficiency equation of 1 minus the VA volume at A over volume at B to the power of 1 minus gamma. Now, remember, in terms of work is done for the path 1 and 3, but no work is done for path 2 and 4, because whenever you have constant volume path, work done is 0 for those paths. Okay. So, and here's an example of the type of let's say the in this diagram here, right? You can see in terms of what we have shows the thermal efficiency of an engine. You can also write it in terms of this, instead of like one, exponent being 1 minus gamma, you can say 1 minus 1 over V, 1 over V2 gamma minus 1. Both is basically correct way of writing it. So you can see, right? So we kind of, talked about this. So you have then intake valve opens and the air fuel mixture enters. And then you basically have the piston moves up and down and compresses the mixture. Then you have a spark plug and ignites the mixture. Then hide gas is pushes the piston downward, right? Because when the gases basically ignite, their temperature increases, so it becomes much hotter, and they start moving faster, and they can basically push the piston down. But afterwards, then exhaust valve opens and the residual gas escapes. The piston moves up and pushes the remaining gas out, and the cycle repeats. Okay, so that's why what you have here is we can end up deriving. We're going to see that I have an example here. I'm going to derive this efficiency equation for you, and this is basically a process that again takes heat at doing one of the isochoric or isovolumetric processes, and dumps heat during one of the, again, constant volume, right? So you can see, right? So during that process, when the heat is removed and added, the volume doesn't change. Okay, then you have two adiabatic processes in which there's adiabatic compression and adiabatic expansion. Okay, and the two important things here is the volume one and volume two, because those are the ones that are used in the efficiency equation. All right, so let's look at then in terms of how we can have the efficiency uh, to basically be represented with that equation. Okay. So again, so we're going to model the energy input and output as occurring by heat in the process from B to C and D to A. So if you go back over here, you can see that when I go from B to C, there's a heat added, and from D to A, there's a heat removed, while the volume remains constant. That means for those processes, I can say that going from B to C, I have an isovolumetric, also known as isochoric process at constant volume. That means I can write QH as NCV, then TC minus TB. Then going from D to A, again, same thing, right? So isovolumetric, isochoric process. So in this case, I have then my QC though, which is then equals to NCV, then TD minus TA, temperature state D minus temperature state A. Okay. Now efficiency is equals to 1 minus QC over QH. Okay, write like that, put absolute values, so make sure that those values are, none of them are negative. So now equals to 1 minus, and QC is N CV, then TD minus TA. QH is N CV, TC minus TB. Okay, then you can write NCV, NCV cancels out. So then 1 minus TD minus TA over TC minus TB. Okay, so these are for those isovolumetric processes. Then what you have here is we also have the processes where we had adiabatic, right? So that means going from B to A, from A to B, it was an adiabatic compression. That means I can write for here is as TA VA gamma minus 1 equals TB VB gamma minus 1. And then for the other process, right, from C to D, then I can write it as TC VC gamma minus 1 equals to then TD VD gamma minus 1. Okay, that means those are for adiabatic compression and adiabatic expansion for the Otto cycle. All right, so then what we have here is from these equations, I can see that when I look at this adiabatic expansion and compression, I can write this then TA in terms of then TB VB over VA gamma minus 1, which then will be TB, let's say V2 over V1 gamma minus 1. That means, A is the first one, B is the second state, right? So going from 1 to 2. And then for this one, for TD, I can write this as TC, then VC over VD, gamma minus 1, which also will be then same as TC V2 over V1, gamma minus 1. Let's say before and after everything. Okay. All right, so now lastly, what I have here is then when I write this down, I can write this as TC, VC over VD, gamma minus 1, VC over VD, gamma minus 1. Okay, in terms of efficiency, remember? So if I look at this ratio over here of TD minus TA and divide by TC minus TB, okay, then I can write it down in terms of, TA and TD that I just got. So I can write this as, so TD, this is my TD, which is TC times V2 over V1, gamma minus 1. Then my TA is then written as TB, V2 over V1, gamma minus 1. And this divided by TC minus TB. Now, from here on the numerator, then I can factor out that ratio of volumes. So this becomes basically V2 over V1 times gamma minus 1 times TC minus TB. And then I divide this by TC minus TB, which then I can see that this ratio, this difference of TC minus TB can cancel out. That means what I have here is this TD minus TA over TC minus TB is nothing but V2 over V1 gamma minus 1. Okay. That means that I can go and write this as 1 efficiency is equals to 1 minus V2 over V1 gamma minus 1. And that's basically in terms of what we have. Or technically, I can also write 1 minus V1 over V2, then 1 minus gamma, okay, by switching the ratio of the volumes inside.